Good evening, dear colleagues. My talk will be dedicated to the structure of the superconducting order parameters in lithium iron arsenide as directed experimentally. I think everybody knows that iron-based superconductors were discovered more than 10 years ago, and now most of their aspects are well described. But there are some exceptions. For example, lithium iron arsenide system shows some troubles that experimentalists have to overcome, and there is a reason why its family is much less intensively studied than others. Due to the presence of active lithium ions, these single crystals degrade very rapidly in presence of even trace amounts of oxygen and water vapors. So about 5 to 10 minutes exposure of single crystal in open air is enough to drop the critical temperature up to 0. So to deal with these single crystals, one have to make experiments in a protective atmosphere. Lithium iron arsenide superconducts in the stoichiometrical state and shows its optimal critical temperature in this state about 18 kelvins. And any doping or lithium deficiency effectively decrease the critical temperature. So this phase diagram resembles that of magnesium diboride. Several ARPA studies show the Fermi surface of lithium iron arsenide and the presence of several superconducting condensates below the TC with strongly anisotropic superconducting order parameter. Of course, several other techniques were used in order to probe the structure of the superconducting order parameter in LIFE-S, but no direct experiment on the determination of the magnitudes of superconducting gap and their temperature dependence was made to date. So this is our motivation. And now we turn to our experimental technique. We used the spectroscopy of multiple underwave reflection effect of planar break junction contacts. This effect occurs in symmetrical junctions of superconductor normal metal superconductor type or SNS junctions. Several theoretical models describe this MAR effect, and if we simulate the IV curve and its derivative, dIdV spectrum, for a semi-ballistic junction with the inelastic scattering length to the contact dimension ratio about 2, we could see an excess current at the wall bias voltage range, the absence of Josephson supercurrent branch, an enhanced zero bias conductance, and a subharmonic gap structure, the series of dynamic conductance dips at certain positions, EV, that are directly determined by the superconducting gap delta, at any temperatures from 0 to TC. So probing symmetrical SNS junctions allows one to directly get the magnitude of the superconducting gap and its temperature dependence. For a real SNS junction introducing small but non-zero probing parameter gamma, only the fundamental harmonic at the position of 2 delta is well visible for each band. So for example, for 3-band superconductor, for 3-gap superconductor, we expect 3 fundamental harmonics at one and the same di and dV spectrum. According to this simple approach by Devereaux and Fulde, anisotropic S-wave gap produces powerful and symmetrical dynamic conductance dips, whereas the D-wave gap causes strongly suppressed and asymmetrical dips. An extended S-wave polar distribution would cause doublet features, whereas the positions of the 2 dips, this one and this one, correspond to the gap edges. The maximum Cooper pair energy delta out is the position of these dips, and minimum Cooper pair coupling energy delta in relates to the position of this dip. The gap anisotropy could be estimated as follows. So this rather wide doublet corresponds to 30% anisotropy. Namely, similar doublets are typical for lithium iron arsenide, as shown here. This is a fragment of experimental spectrum, and the positions of two dips directly determine the two gap edges. The junctions were produced by planar break junction technique. The sample, made as a thin rectangular plate, the single crystal, was attached to a U-shaped springy sample holder and then cooled down. After cooling down, the sample holder was mechanically curved. Thus, the sample splits along the AB planes with the formation of steps and terraces on cryogenic clefts, acting as a junction between two superconducting banks separated by a constriction of high transparency. In the used geometry, the current always flows along the C direction through our junctions. Such planar break junctions have a lot of advantages, and the most important advantage is the full probe connection and the location of microcrack far from current and potential leads and deep in the bulk of the sample. This prevents the constriction from impurity penetration, from surface degradation, and from overheating due to the current injection, and therefore providing high resolution. Under the fine-tuning of the holder curvature, the cryogenic clefts slide onto each other, thus varying the area of the break junction. So we could easily mechanically readjust of the junction and to form up to several tens, whereas SNS junction is in one and the same sample due to one and the same cool down, in order to check the data reproducibility and to collect the data statistics. Now let's proceed with the experimental data, and first we turn to the normal state properties above the critical temperature Tc. Here are the IV curves of one and the same break junction of symmetrical N constriction N junction measured above the critical temperature Tc. The curves are strongly nonlinear, but note they are symmetrical about the zero bias and show no hysteresis. So we don't attribute this nonlinearity to the heating. The nonlinearity gradually decreases and the CVC becomes ohmic at temperatures about 18 to 100 kelvins. This nonlinearity is also present on the DI-DV spectrum. The spectra are shifted vertically by hands for clarity. The dashed line corresponds to the critical temperature Tc, and we could see pronounced dynamic conductance hump at lower bias voltages. This hump gradually smears and almost disappears at higher temperatures. At lower temperatures below Tc on this strongly nonlinear background, the sharp structures caused by multiple Andreev reflection transport also appear. The gap dynamic conductance dips and Andreev enhanced zero bias conductance peak. According to the classical tunneling approach by Gever and Megerle, the current through the tunneling junction in the normal state is determined by the density of states in the normal state banks. So if we observe such strong nonlinearity, as the most trivial reason of it, one could suppose the nonlinear electron dose density of states distribution that shows a peak near the Fermi level, which could be caused, for example, by a flat band presence in the vicinity of the Fermi level. Now let's detail the Andreev structures that appear below critical temperature Tc. Here are the raw experimental data. On the bottom there are current voltage characteristics. They show no supercurrent branch but excess Andreev current, and raw dynamic conductance spectra below and above Tc for the two junctions. On their nonlinear background, the Andreev dips attributed to the three superconducting order parameters are well visible. In order to detail the Andreev structures, we suppress this nonlinear normal state background. So here are the same curves with the linearized normal state DIDV. At the lowest bias voltages, there are rather pronounced and sharp dips, which correspond to doubled small gap to delta S. Comparing with the ARPES data, ARPES tells us that the smallest gap develops on the largest barrel of the Fermi surface, the outer hole barrel, so we could attribute this order parameter also to the outer hole barrel, and its value is about 1 millieV, and due to the large amplitude of these dips, we obviously expect an S-wave symmetry of this gap. At higher bias voltages, this nice doublet appears, it's rather wide, and the positions of the two dips, the inner and the outer, directly determine the energies of the second superconducting order parameter, its edge magnitudes to delta L, from 2 to 3 millieV. Again, comparing with the ARPES data, we could attribute it to the electron sheets and sketch the polar distribution of this superconducting order parameter. Note that our technique is able to directly determine the energy characteristics, the energy values of delta in and delta out, but the certain gap distribution is just supposed. We supposed a fourfold distribution, so this is just a sketch. And finally, at high bias voltages, a small minor splitted doublet also appears attributed to the third superconducting order parameter, and according to ARPES, the largest gap develops on the smallest barrel, so we attribute it to the inner barrel near the gamma point and call it delta gamma. So its anisotropy is about 10%. And also we could sketch an extended S-wave symmetry. Summarizing the directly determined energy characteristics for various junctions in various samples with the range of local critical temperature, and depicting each energy position as a semi-transparent bar, we could plot such color histogram. Plotting these data in terms of the VCS characteristic ratio to delta on KTC, one could see that the data dispersion for the large gaps is much less, so the accuracy increases. This means the gaps scaling with the critical temperature in this interval. Their characteristic ratios for the gap edges are summarized here. The small gap shows no signs of anisotropy. The middle gap, delta L, is moderately anisotropic, with about 30% anisotropy, and the largest delta gamma is mineral splitting with about 10% anisotropy. The variation of local critical temperature could be attributed to the local lithium deficiency in the samples of nominally stoichiometric composition. Turning to the literature, we could summarize the values of superconducting order parameter in lithium ferroarsenide single crystals in terms of 2 delta on KTC ratio versus critical temperature. The ARPES data correspond to one and the same TC, 18 kelvins, but for clarity, these data are shifted horizontally. The connected symbols illustrate the gap anisotropy, and the color correspond to the certain sheet of the Fermi surface. Again, ARPES observes the largest gap on the smallest barrel, the smallest gap on the largest barrel, and the middle gap in the electron bands. Other techniques, the data obtained by other techniques are obviously grouped into three ranges. Scanning tunneling microscopy observes the largest gap parameter and the middle gap, whereas bulk techniques such as specific heat and lower critical field and surface technique, infrared reflection spectroscopy and surface impedance measurements revealed the middle gap and the small gap. Now, putting here our data by stars and depicting the anisotropy as the vertical bar connection, we get very good correspondence. Our delta gamma data coincide with STM data and appear in the top range. For the middle gap, delta L, our anisotropy range, about 30%, exactly covers the range of the values obtained in the literature. And for the small gap, we haven't observed any anisotropy, and our value lies just in the middle of the literature data. All these to delta on KTC ratios keep almost constant with critical temperature, so all gap energy parameters are scaled with critical temperature TC in the studied TC range. Now let's check the temperature evolution of the determined energy characteristics. We measured the dynamic conductance spectrum of an SNS junction with temperature increase. Here the normal state nonlinear background is suppressed, so the curve corresponding to TC is just linear. The normal resistance is the same and keeps constant with temperature up to TC, but for clarity the spectra were shifted by hand vertically. With temperature increase, all the features caused by incoherent multiple Andreev reflection transport gradually vanish. I mean the enhanced zero bias conductance and the Andreev structures. They shift toward zero. Tracing the doublet of the largest gap delta gamma, we directly obtain the temperature dependence of its edges by red points. Also, we plot the temperature dependence of the gap anisotropy in the inset by red. The anisotropy, the ratio between these energy parameters, is exactly the same until critical temperature TC, and keeps about 11%. The same was done for the doublet for the middle gap delta L. Here is the temperature dependencies of delta L out and delta L in gap edges, and its anisotropy, about 30%, is also almost independent on temperature. And finally, the temperature dependence on the small gap is shown by orange triangles. Here are similar data for another SNS junction, thus showing the reproducibility of the data. Reproducible are the gap values, their characteristic ratios, the temperature behavior of anisotropy, it is almost independent on temperature, and the shape of the temperature dependencies. All the curves pass below the single band BCS-like curves, and in general the shape is typical for a moderate interband interaction as compared with intraband interaction. Well, in conclusion, we have studied more than 20 single crystals of lithium iron arsenide. Above critical temperature TC, we observed strongly non-linear normal state properties, which could be attributed to presence of density of states peak in the vicinity of the Fermi level. And below TC, we directly and reproducibly determined three superconducting order parameters, three bulk gaps, determined their 2 delta on KTC ratios and resolved the anisotropy of delta gamma and delta L, and found no signs of delta S anisotropy. And the temperature dependencies also directly measured are also reproducible and correspond to a moderate interband interaction. Also, I would like to thank our colleagues from Dresden for partial sample providing the support by Russian Foundation for Basic Research, and also I would like to thank the organizers for the possibility to make a talk in this nice place in this conference. Thanks for your attention.
Thanks, nice talk. I'm not in the field, just a naive question, perhaps. What is the N in your case? I did not hear it, or I missed it. Then the N layer, when you do SNS junction, what is the N layer? Is vacuum or is something else?
Oh, he's asking where is the N layer?
The normal layer.
The normal layer is just a model. We have a conscription separated two superconducting bands. And this conscription in lithium iron arsenide and in other families of iron-based superconductors is electrically equivalent to a thin normal metal layer.
So which metal in this case?
It is just a model. It is a constriction of extremely high transparency.
So I don't understand. You have something there or not?
No, it's
just vacuum.
Just a crack, broken chemical.
And what is the dependence of your signal on the thickness of this crack, let's say? Or you know?
We could control the resistance of the junction. So resistance, typical resistances are from 1 ohm to 100 ohm.
So what do you like to prefer, a thin N or a large N, or what is it? There is some optimum value, I don't know.
There is no hole between two superconducting bands, they just slide onto each other. So this is just broken chemical connections.
Okay, another question?
Did you measure this multiple deep structure in magnetic field?
No, we haven't.
Yes? No?
No, we haven't.
For this material, for other materials?
We probed these structures in magnesium diboride in rather low magnetic fields and haven't observed any difference.
Okay, last question.
It is known that iron-containing superconductors are very sensitive to external pressure, and it is also known that break junction technique produces additional stress and pressure. How your data, for example, on the superconducting temperature coincides with another experiments?
Our local critical temperatures, the temperatures where the features caused by Andreev transport disappear, is consistent with bulk measurements, resistive measurements, and magnetic.
The same critical temperatures?
Yes.
That's a bit strange also.
Due to the sliding of cryogenic wax in layered compounds, we don't expect very high pressures.
Yeah, they are not pressing isostatically, so probably. But in principle, the sample is free on one end, so it's free to bend. So maybe this is the explanation.
That is actually bringing the question I always wanted to ask. Not regarding how you create the context, but have you ever tried to look how you do it? For example, put it in a scanning electron microscope, because you already have a notch, you know where it should to crack, and look actually under the microscope how it goes. I'm not telling about tunneling, scanning tunneling, but just scanning electron microscope should gives you idea how exactly your sample's cracking, especially when it's polycrystalline, right? You can see certain crystals to go and to split in certain directions. Have you tried or been thinking about doing that?
It is impossible to look into the junction during the experiment. So we
No. You can if you put it in scanning electron microscope, and if you actually start to break it, right?
Yeah.
You immediately see what is happening with your break, with your notch. That was already done for the normal break junctions.
Yes, we have seen the electron microscopy, and yes, there are clear steps and terraces on the cryogenic rafts. The typical size of terraces is about 100 nanometers. As in other layered compounds. We also do it for polycrystalline samples and observed such steps and terraces on the surface of splitting crystal grains.
I think you made that in MGB2, in the case of MGB2, or if I remember, I am wrong. Didn't you see with the microscope, electron microscope, after the breaking in MGB2?
Yeah.
Yes.
Yeah.
They did already, yes. I think she does not have it here. Okay, so I have just a small question, but have you any idea of why this excess conductance persists up to this high temperature, up to 180, 100 temperature, 100 Kelvin? You see this. Do you have any idea what is the?
We haven't attributed it to heating. We haven't attributed it to phonon or backspectrum. So the most trivial is density of state speed.
Yes, because
But it is reproducible. The nonlinearity is so strong in lithium iron arsenide. We haven't observed such strong peak in other iron rate superconductors, nor in magnesium debris, nor in cuprates.
Okay, so it's a feature of this material.
It's a feature typical for lithium iron arsenide.
Okay, thank you.
It's typical feature for metallic point cloud.
Okay.
Yes, but not so strong.
Okay, so I think so. The question is, we still have time. You must give him the.
How in your setup can be separate?
How in your setup can be separation the regimes of Josephson and SNS and Reeve spectroscopy?
We could obtain both regimes and judge on the ground voltage characteristic and the
Sure.
How it's in some positions these regimes, how they separate by.
In the Josephson regime, we observe the lack of current and Josephson supercurrent branch.
But how they in different positions, or how they separate both regimes? How to from another regimes by
Using the mechanical readjustment, we could vary the contact resistance and transparency. And also typical features of the materials incorporate, so the Josephson characteristics are typical, but in iron-based superconductors we obtain only unreef ones. It depends on the construction transparency. Josephson regime corresponds to the extremely low transparency. And here the transparency is extremely high, more than 90%, with that very strange less than 1.5.
maybe.
Okay, I think we can stop here. I would like to thank all the speakers of the session, and we can close the session. Thank you very much to everybody.